Hi, in this video we're going to talk about the relative rate of change. Okay, so far we've talked about average rate of change and how we get the derivative that way, and we can actually think of the derivative as the instantaneous rate of change. Here we want to think about the relative rate of change. Remember that relative change was defined earlier by the formula f of b minus f of a divided by simply f of a. So it's not the average rate of change. It's not the derivative. It's a different thing. We take the difference between the values at a and b and we divide by a. This sort of represents a percentage growth rate. Now we'd like to do this instantaneously, so we'd like to average this over a very small interval. In particular, what we'll do is divide that by b minus a. So we take that, divide by b minus a, and now notice that if we do some algebra, this is really the same as f of b minus f of a divided by b minus a divided by f of a, which looks kind of strange, but bear with me. Now if b is very close to a, then the numerator here of this three-story fraction is going to get very close to the derivative. So this is approximately the same as f prime at a divided by f of a. So if we want to get it turns out that if we want to take the average rate of relative change, that's what this quantity is, that's in the limit as b gets closer to a, this quantity, which we'll call the relative rate of change. Okay, so that's what we have to remember here. Now the relative rate of change is actually something we've already seen before. The relative rate of change is constant if and only if the function f is an exponential function. In particular, if you have an exponential function, if f of t is, say, equal to f of 0 times e to the kt for some constant k, then, miracle of miracles, this number here is actually k. Okay, so this constant k is actually the relative rate of change. Okay, so how is this relative rate of change used in word problems? So let's look at an example. So according to the National Oceanographic and Atmospheric Administration, the average density of CO2, carbon dioxide, in the atmosphere was 392 parts per million, which means that out of every million molecules, 392 of them were carbon dioxide. And the rate of change in the average density was 2.4 parts per million per year. Of course, it's a rate of change, so it should be per time period, and this is year. And we're asked, what is the relative growth rate? Well, how do I interpret this problem mathematically? So if I think of f of t as the average density of CO2, then the first clause is telling me the average density in the atmosphere was 392. So at my particular time, in this case it's actually 2012 data, which I should have said, that's equal to 392 parts per million. Now the second part, and the rate of change in the average density was 2.4 parts per million. That's a derivative statement because I'm talking about the rate of change. So the derivative, f prime, in the year 2012 is equal to 2.4. Okay, now what's the relative growth rate? Well, the formula is relative growth okay, this is the formula to memorize, is f prime, in this case 2012, divided by f of 2012, which is 392 divided by 2.4. So that's all you have to do is take the derivative at your point, divide by the value of the function. That's your relative growth rate.